Welcome back to the continuation of Module 4 on the inputs needed to use the Pavement ME Design software. As a reminder from Module 1 on the course schedule, the next part of Module 4 on the input parameters are the truck traffic inputs, submodule 4.3. Module 4.3 will overview and discuss the truck traffic inputs required by the Pavement ME Design software. We all know truck traffic or traffic is an important input variable to basically any pavement design procedure, including the MEPDG. The focus of this submodule is to overview the truck traffic inputs needed by the Pavement ME Design software for pavement design. There are 4 learning outcomes for this submodule. The first is to list and define the truck traffic inputs required for Pavement ME Design. The second is to explain how to determine the traffic inputs. The third is to describe the simulation of truck traffic for pavement design. And finally, the fourth is to describe the impact of selected truck traffic inputs on the predicted distress itself. Now, the MEPDG Manual of Practice, Chapter 8, overviews and discusses determining site conditions and factors that are needed for pavement design. Section 8.1 of Chapter 8 is on the truck traffic. Section 8.1.1 provides a discussion of roadway-specific inputs. Section 8.1.2 are the inputs that can be extracted from weighing and motion data. And Section 8.1.3 is on truck traffic variables which are not included or can be extracted from the WIM data itself. So now with that, let's go to the Manual of Practice itself and then look at Chapter 8 on truck traffic. So we'll go down Chapter 8, determining site conditions and factors. 8.1 is on truck traffic, and this basically discusses the different truck traffic that's required for both new design as well as rehabilitation design. Table 8.1 and 8.2 provide suggested minimum sample size requirements. 8.1 is specifically for the WIM data or the weighing and motion data to determine the normalized axle load spectra. And Table 8.2 is the minimum sample size requirement for looking at the normalized truck traffic volume distribution from automated vehicle classifier data. As we mentioned previously, 8.1.1 are the inputs that are roadway specific to a specific roadway. We'll get into each of these as we go through the submodule. 8.1.2 are on those inputs that can be determined or are determined through the WIM data and can be extracted from that data for use in Pavement ME. Table 8.3 is the normalized axle load spectra from the WIM data that's included in the AASHTO-aware Pavement ME software. Basically, these are the default distributions that are the default normalized axle load distributions that come with the software. So the user can select any of these. One is referred to as NCHRP 1-37A, which was the original one included with the software. There are 3 others, one referred to as heavy, another as typical, and another as a light axle load spectra, and then an overall global axle load spectra, which is considered the typical for typical classification. So these are the ones that the user can select directly from the software itself. Obviously, if the user has WEM data and has analyzed the WEM data for specific roadway segments, the user can import any of those directly into the software. Figure 8.1 is simply a comparison of 5 normalized axle load spectra defaults for vehicle class 9 tandem axles. And this simply shows the percent of axles within each load interval as a function of the tandem axle load interval itself. Figure 8.2 is simply an expanded graph of those axle load spectra that are on the heavier side, or the tandem axle load interval for class 9 trucks that are on the heavier sides. And you can see some of the differences between the axle load. And we'll get into this specifically for the sub-module. And then we go through a definition of the different terms that are used. Table 8.4 is another very useful table that is included in the Pavement ME software. This table is referred to as the Truck Traffic Classification Groups, or TTC groups, which are descriptions of truck traffic volume distributions that are default values with the Pavement ME software. And basically there are 17 of these TTC groups that provides the average or default normalized axle load spectra for different types of roadways, as well as a different mix in the truck traffic. And we'll explain this a little bit later in the submodule. And then table 8.5 is simply a definition and description of some of the truck traffic classification group numbers. So this provides how one might select a TTC group based on whether there's buses in the traffic stream, whether there are multi-trailers, and then the single, tandem, and single unit trailers mix within the truck traffic stream. So it provides some information for a user to select the normalized truck volume distribution for a specific roadway. Then 8.1.3 is the truck traffic input and input variables that are not included or can be extracted from the WEM data. And those are provided as well as defined in the manual of practice itself. So with that, we'll get back to the presentation and then continue. So as we previously noted, section 8.1 is on truck traffic. We have roadway-specific inputs, which is the average annual daily truck traffic, the growth of the truck traffic itself, percent of trucks in the design lane, percent of trucks in the design direction, and operational speed. The inputs extracted from the WEM data are the axle load distributions, the axle load configuration, the normalized truck volume distribution, the monthly distribution factors, and the hourly distribution factors. Section 8.1.3, or truck traffic not included in WEM data, which include dual tire spacing, tire pressure, lateral wonder of the axle loads, and the truck wheelbase. These truck variables are included in the Pavement ME Design software and are in a slightly different format and are discussed in more detail within this module. Truck traffic is an important for the MEPDG as well as other mechanistic empirical and empirical-based design procedures because truck traffic has a significant impact on the material and/or layer property requirements as well as layer thickness. Truck traffic volume and weights impact the minimum layer or minimum requirements to ensure an acceptable performance of a pavement section. The Pavement ME Design software combines the number of trucks and the weight of the trucks with the climate data just delivered under Module 4.3 and the layer properties to predict pavement damage and distress throughout the design period itself. The type of trucks and axle configurations are important to estimate pavement damage and distress. Most of the truck traffic input variables are determined from the truck vehicle classification data and the weighing in motion or WIM data. The spacing of the axles, the spacing of the dual tires, tire pressure, the number of single axles, tandem axles, tridem axles, as well as quad axles, are important to determine and predict calculate pavement response for predicting pavement distress and roughness. The introduction to the traffic data is to reinforce the data required as input variables to the MEPDG-based procedures and is no different than the factors needed and used to calculate the number of 18 kip equivalent single axle loads for the empirical AASHTO design procedure as well as other mechanistic empirical based procedure. So the traffic data that is required by the Pavement ME Design software is basically no different than the traffic data needed to calculate 18 kip equivalent single axle loads. In fact, the software does calculate the number of 18 kip equivalencies throughout the design period. So even though it looks like there's a lot of data required to simulate truck traffic, in actuality it is basically no different than what's required for the 1993 AASHTO pavement design procedure or the empirical pavement design procedure. So the truck traffic and or total traffic is defined in terms of the FHWA vehicle classification definitions, going from a Class 1 motorcycles all the way up to a Class 13 multi-trailer and with 7 or more axle trucks or so. So from very light traffic to very heavy trucks. The Pavement ME Design software, however, is only based or uses the vehicles from a vehicle class 4 for buses for the and through 5, 6, 7, 8, all the way through 13 for the multi-trailer 7 or more axles under the trucks. So class 4 through 13 is what is required for the Pavement ME software. The vehicle classifications 1, 2, and 3, which is very light vehicle traffic, pickups, cars, motorcycles, those are not included in the Pavement ME Design software. Some agencies use more or a slightly different truck or vehicle classification definition. If an agency uses more or a different classification number, those have to be converted back to the FHWA vehicle classifications designations that are included in the software. Now, this is a screenshot of the truck traffic data used by the Pavement ME Design software. The truck traffic is divided into multiple tables or tabs regarding truck volume, magnitude, and distribution, truck weight, axle configurations, the lateral distribution of trucks, and other input variables that are needed for mechanistic empirical pavement design. So with that, we are going to open the software and show where the truck traffic. So we're going to get to the truck traffic input variables. And as noted previously, there's a series of tabs with the truck traffic screen that provides the data. And we'll go through these very briefly. So the first is the average annual daily truck traffic. It's the two-way AADTT that's entered by the user. We then have the number of lanes in the design direction. They can be anywhere from 1, 2, 3, 4, however many lanes are in the design direction. And these would be considered the through-way traffic. And then percent trucks in the design direction, percent trucks in the design lane. And if we have obviously one lane in each direction, this would be 100% of trucks in the design lane. So we're going to leave this though at 95. And then the operational speed of the trucks. We'll define the operational speed as well as these other variables as we get into the software or as we go through the software inputs in the under Module 4.3. The next is what's called truck traffic capacity. What this is intended for, the truck capacity level basically has no impact on the distress predictions when the roadway has not reached its capacity limit. So this tab is to provide the user with putting in information to determine whether or not the truck traffic will exceed the roadway's capacity. If the roadway or if the truck traffic exceeds the capacity of the roadway, the truck traffic will no longer increase. So in that case, when the capacity of the roadway is achieved or exceeded, there is no further increase in truck traffic, and so that will have an impact on the predicted distresses for both flexible as well as rigid pavement design. So again, the truck traffic tab is only for use in determining whether the roadway or the truck traffic will exceed the roadway capacity. The next tab is the axle configuration. This is the average axle width, tandem axle spacing, dual tire spacing, or the spacing between dual tires, quad axle spacing, tire pressure, and tandem axle spacing. These are all default values, and it is encouraged that the user use the default values unless different values have been derived for special roadway segments that may be carrying atypical types of trucks that are the heavier trucks. Okay, so next is the lateral wander. Lateral wander is the design lane width, the mean wheel load location where the wheel loads are located relative to the edge of the pavement, and then the truck traffic or the truck wander standard deviation. In other words, the lateral distribution of the truck traffic or the axles. And we'll get further into each one of these, but these are the mean wheel location and the truck traffic wander standard deviation are basically default values. And those default values are encouraged for use by the users unless they're special situations like narrow lanes and or wider lanes for the truck traffic that might impact the mean wheel load location and or the truck or the traffic wander standard deviation. So we'll get into the definitions, as I said, a little bit later and how those are used. The wheelbase. This is a screenshot or the screen of the wheelbase. The average spacing of the short axle, average spacing of medium axles, average spacing of long axles, percent of trucks with short axles, percent of trucks with medium axles, percent of trucks with long axles. And the wheelbase is only needed for rigid pavement design. Even though these are shown in the screens or for the tabs for flexible pavement design, these are not used to calculate pavement responses directly. So the vehicle class distribution. Vehicle class distribution simply provides the normalized volume distribution for class 4 through class 13 trucks. Both the average normalized distribution and then the growth rate as well as the growth function are included. So we can easily change the growth rate and the growth function by simply clicking on that button. We can go in for have a different growth rate and use a growth function of none, linear, or compound, and then apply it. And then that gets applied to all of the truck classifications 4 through 13. The user can also enter individual values, and the growth rate as well as the growth function could be set differently for different types of trucks. So, and we can change this to 0 and put this in as none. And so there's different options that the user can use in entering how truck traffic is going to grow over the design procedure. Normally, it's more common just to apply a standard growth rate as well as a standard growth function to all vehicle classifications 4 through 13. The other item before we go forward that we will note is the load default distribution or the truck traffic classification groups that we have previously mentioned in the presentation. So if we click on this then shows us or provides default values for different truck traffic classification groups. These are defined by the expected use, whether it's recommended or not, for depending on the use, of the truck traffic classification group. And again, there's 17 of them, 1 through 17. And then for each group, there's the category of buses in terms of percent, category of multi-trailers, and then the category of the different single trailer or the combination of single trailer and single trailer unit trucks. So the user can come in and see, okay, if we were on an interstate, the asterisk are those TTC groups that apply to, again, principal arterials, interstate, and freeways and defense routes. So we could come in and select one that applies. We can also, to show this, go down to local routes, and you can see the recommended TTC groups are now more on the lower multi-trailer truck traffic. And so we can then select a TTC group that might be applicable to our roadway segment itself. The screen down here is as we change on different groups, the class percentages are going to change, and the user can view what the normalized volume percentages are for each of these TTC groups that are selected themselves. So principal arterials, maybe go down to a TTC group of 10, which is the less than 2% buses, about 2 to 10% multi-trailers, and the mixed truck traffic is mixed truck traffic with about equal percentages of single unit and single trailer trucks. And then for that TTC of 10, this shows the specific values of the normalized truck volume distribution factors for a TTC of 10. So this provides a lot of knowledge to the user for selecting the TTC group when little information is available. So that's the vehicle truck class data is provided. Now the monthly adjustment factors, and basically this shows each of the month, January through December, and the monthly adjustment factors by truck class. These are the defaults that are set to 1, and so the cumulative total for each class needs to total 12 on the monthly adjustment factors. In many cases, agencies have generated specific monthly adjustment factors for each class. You can have some roadways have seasonally dependent truck traffic, others have seasonally independent truck traffic. And so those can be imported, but the important part to remember is that for each vehicle class, the monthly adjustment factors need to add up to 12 because there's 12 months. And this simply distributes the number of Class 9 axles on a monthly basis throughout the year. And that is done for each truck class. Next is the axles per truck, and this is simply each of the vehicle classes 4 through 13, the number of single axles per class 4, number of tandems per class 4, the number of tridems, and the number of quads. So, for example, class 4 can either have 2 singles or a single and a tandem. And so This is determined from either the weighing and motion data or the automated vehicle classifier data to look at the number and type of axles over a period of time. So these do not have to be whole numbers or even to the nearest half of a whole number because they come directly from the data itself. These are the default values that come with the software. The default values included in the truck traffic were derived or determined from an analysis of the weighing and motion data as well as the vehicle volume data from the automatic vehicle classification measurements at the long-term pavement performance data site. There were about 280 sites that were used to derive these default values for the different input values. But the user can change these based on their own data or an analysis of their own data. The next is the axle weight distributions. Okay, and this is simply the axles, single, tandem, tridem, and quads for the different vehicle classes. So go down to the common class 9, which is the 18-wheelers, and we can look at the number the axle weight distribution for the quads in January, the weight distribution of the tandems, or the tridems, and then the tandems, and then of the singles. So the user can quickly scroll through and determine either for the defaults or from the data imported by the user on the axle weight distribution for each of the truck traffic and look at the distributions of singles, tandems, tridems, as well as quads, if there are any tridem and quad axles within the traffic stream for a specific vehicle class. Now, very briefly, remember that we want to, before we show the importing the data, this just simply shows what some of the data that's in the defined by the different axles, the month, and then the vehicle class, so the user can quickly go through and make sure the data that the user is importing is the data the user wants to import. It's typically not used for the default values, but when agencies import their data to make sure the correct file was imported. So going to this now, we want to look at the axle load distribution, and the user can import the NCHRP 137A defaults. The 138A defaults were defined from the initial global values defined from the long-term pavement performance program, at least initially. There is an importing of the updated long-term pavement performance defaults, and these can be defined or defined as global, heavy, typical, and light, and then the user can import their own axle load distribution themselves. So typically and when we get to the back end of the presentation, we'll go through the definition of these for the user selecting one or the other. We'll just click on the 137A defaults, and then those will be imported into the Pavement ME program itself. So that's basically the axle load distribution. So the hourly adjustment factors. The hourly adjustment factors are only used for rigid pavement design. This provides the time of day and the percentages of the total truck traffic within the time of day. Obviously, they all have to add up to 100. And again, these are only used for rigid pavement design. The traffic charts, the user can generate the charts directly and look at the cumulative trucks throughout the design period, truck growth by class group, and do a quick review and look at the truck traffic and how it's going to progress or accumulate over time. Truck growth by class, the cumulative trucks by vehicle class, both directions and in all lanes. And then here's the cumulative rigid, since this is an example we started with for rigid pavements. This would be the cumulative rigid equivalent single axle loads. If we were doing a flexible pavement design, this would be cumulative flexible equivalent single axle loads. And this just shows the number of rigid ESCLs over the design period, going from 0 to whatever the design life is, in this case, 20 years. So basically, that's the different tabs within the software. We'll now go back to our presentation, and then we will continue. So, traffic data and its use in the Pavement ME Design software. We have the average annual daily truck traffic, and then the truck class volume distribution, the seasonal as well as the hourly factors, and the seasonal is referred to as the monthly distribution factors, and then the hourly distribution factors. Both of these define the total volume of axles in the design lane and throughout the design life of a pavement. The next is the axle weight distribution. These are the axle weight to be used for the critical response calculations for predicting the stress of flexible and rigid pavements. The next is the lateral wander of trucks, the axle lateral variation for critical response calculations for predicting the stress over time. And the fifth is the axle configuration. This is the wheel load locations, in other words, individual wheel load locations for critical response calculations. And as you will remember in Module 2, the Pavement ME Design software uses load superposition for flexible pavement design for calculating the responses under as well as between different axle loads and axle load location using elastic layer theory. And then the sixth, traffic capacity. It's the capacity of the roadway limits for the volume of trucks. And again, it doesn't have an impact on the predicted pavement distresses unless the capacity of the roadway is exceeded. Now let's focus on the average annual daily truck traffic and other variables in the Pavement ME Design software. So the AADTT and other roadway-specific variables. We have the two-way average annual daily truck traffic, the number of lanes in the design direction, percent of trucks in design direction, percent of trucks in the design lane, and the operational speed of the design trucks. And so the percent of first of all, the two-way average annual daily truck traffic and the number of lanes in the design traffic are required inputs to the Pavement ME software. The Pavement ME software requires the ADT in both directions for the roadway, and then the number of through lanes in that direction. In the picture on this slide, the number of lanes in the design direction would be 3. The number of lanes should exclude any turn lanes and exit or entry lanes for some urban routes. The turn lanes and the exit or entry lanes for the facility or roadway can be designed separately using truck traffic expected for those lanes. For the Pavement ME, one lane in one direction can be used for the truck traffic. So now directional distribution factors. The directional distribution factor is the percentage of total trucks in the two directions of an undivided or divided roadway across all through lanes. Most agencies assume a 50-50 split between the different directions, which is a good assumption for interstate roadways. However, some lower volume roadways generally start to diverge from the 50-50 split. The MEPDG Manual of Practice provides some guidance on the different directional distribution factors by roadway classifications, which were derived from traffic data collected within the long-term pavement performance program. For the example shown on the screen, the directional distribution factors for this specific roadway is 45% in one direction and 55% in the other direction. And again, that is only the truck traffic. That is not all vehicular traffic. The directional distribution factors only apply to the truck traffic. Lane distribution factors. The percentage or ratio of total truck traveling in one lane in one direction. The lane distribution factors are dependent on the number of lanes in one direction. The MEPDG Manual of Practice provides some guidance on the different lane distribution factors by number of lanes, which were derived from the truck traffic collected within the long-term pavement performance period. Operational speed of the design trucks. First, some examples on what the MEPDG can and cannot do to answer questions on how truck traffic impacts pavement performance and how the MEPDG can be used to answer different questions in day-to-day practice of an agency. Specifically, one of these limitations is on the speed of the trucks. Pavement ME applies the operational speed of the truck to all different truck classes, going from a class 4 to a class 13. The truck speed, however, does impact the material layer response properties. So the average speed of the heavier or larger trucks is recommended for use in the Pavement ME Design software. So you can have a class 5, a class 4, 6, or 7 type trucks that typically can have higher speeds for different facilities as opposed to a truck class, say 9, 10, 11, 12, and 13. But since the loads are typically heavier for the larger trucks, the average speed of those heavier trucks should be applied or should be determined for all the truck traffic. So factors to consider. Posted speed limit. What is the roadway speed limit? Steep grades, congested truck traffic, and or controlled sections or speeds, roadways that include stop signs or lights like users can run into in urban and even some rural roadways. So these items should be considered for determining the average or design speed of the heavier trucks. And the speed of the heavier trucks are defined or assumed to be equal nighttime versus daytime, as well as January through February, all months, and all times during the day. Truck traffic now, the truck class volume distribution, the seasonal or monthly and hourly distribution factors will be defined as follows. So we have normalized volume distribution factors, we have monthly volume distribution factors, and we have hourly distribution factors. The normalized truck volume distribution factors is the percentage or ratio of an individual truck volume within the total truck volume or average annual daily truck traffic. The normalized vehicle volume distribution is determined from the WEM data and or vehicle classification data that's collected over time. The graph shown on this slide is a bar chart illustrating an example of a normalized vehicle volume distribution. The volume distribution percentages vary by type of roadway, which could include interstates, primary arterials, minor arterials, and local collector routes. The normalized vehicle volume distribution do impact pavement performance. Historically, vehicle classes 5, 9, and 13 have been used as the three primary vehicle classes to define especially the truck traffic classification factor. So what's shown on this bar graph is simply the interstates in basically the darker blue, primary arterial, which is the crossed hatch, minor arterial, reverse crossed hatch, and then the local collector routes in the yellow, solid yellow or orange type bar graph. And then class 4 is the buses, class 5 single units, class 6 is single units with a tandem, class 7 single units with a tridem axle, class 8 is a single unit truck with 2 singles and a steering axle, class 9, which is combination of tandems and single axle or single steering axle. Class 10, which is the tractor trailer similar to a class 9, but with a tridem axle. And then class 11 is the multi-trailer, as well as class 12 and 13, the multi-trailer tractor units. And this just shows the distribution comparison from an interstate down to local routes. As you can see, for the interstate, class 9 has a much higher percentage as compared to the local percentages, and then the class 5 for the local routes is much higher as opposed to the interstate type truck traffic. So this is just to give a user an indication of the normalized volume distribution and how it's used in Pavement ME. The default normalized volume distribution factors, these are the truck traffic classification groups embedded in the software that we demonstrated or illustrated when the software was open. So we're not going to define each one of these. The important part, remember, in the manual of practice, there is a table that defines each of these and provides a more verbal description of the type of truck traffic that would be applicable to each truck traffic classification group, and then also provides from these asterisks, remember, that for going from primary arterials, interstates, and freeway down to local groups, which of these TTC groups are applicable from a functional roadway classification grouping. So the user is referred back to the manual of practice for selecting the truck traffic classification group for a specific roadway, under the condition where the user would not have the average normalized volume distribution that's been collected from data along the truck data along the roadway. Now, monthly truck volume distribution are the ratios of total annual trucks within a specific month on the average. The monthly truck volume distribution factors should add up to 12 for an individual truck class. The default values included in the MEPDG are 1.0, as we illustrated or demonstrated when we opened the software. Most sites will deviate from that default value, but will not have a significant impact on the final design or predicted distresses. The monthly volume distribution factors are determined from the WIM data and/or vehicle classification data collected over time. In most cases, the monthly truck volume distribution factors are derived from vehicle classification data. As an example, the monthly truck volume distribution factors shown on this slide are considered seasonally independent. In other words, most of the monthly adjustment factors are very close to 1, and seasonally dependent, where the monthly adjustment factors are significantly different from 1.0 or the default value. Seasonally independent sites usually represent interstates and expressways, whereas seasonally dependent are typically represented by secondary arterials or local collector routes. Sites where traffic is seasonally dependent and usually represent local routes which carry a high percentage of local commodities. For this site shown on the slide, the truck traffic is more heavily concentrated in the summer months as opposed to the winter months, with the exception of Class 13 larger truck traffics for this specific roadway. Monthly truck volume distribution factors. This graph included on the slide compares the predicted jointed plane concrete pavement percents cracked slabs along the y-axis using the two monthly truck volume distribution factors shown on the previous slide, kind of as a reminder. Seasonally independent versus seasonally dependent monthly distribution factors. And so this slide is simply looking at the impact of cracking when we have seasonally dependent and independent monthly adjustment factors for Portland cement concrete fatigue cracking of a jointed plane concrete pavement. So this is seasonally dependent, and at a 90% reliability, we would predict 14.5%. If we had seasonally independent truck traffic, we would predict 10.15% crack slabs at a 90% reliability. The mean value for seasonally independent would be 2.72% crack slabs, while 5.7% crack slab it was predicted for seasonally dependent monthly distribution factors. So it does make a difference, but the difference is not as important as some of the other material-related inputs that we'll cover later in Module 4. The truck hourly distribution factor, these are the average default values for rigid pavement design, percent of total truck traffic from the traffic counts for different intervals during the day, midnight to 6 a.m., 6 a.m. to 10 a.m., and so on from then 8 p.m. to midnight. This is needed for rigid and composite pavement design. These are not needed for flexible or semi-rigid pavement design. Remember, the hourly truck volume distribution factors is used to determine the number of trucks operating during the time of day to calculate the tensile stresses in the top and bottom of the concrete slab. The hourly volume distribution factors are usually determined from vehicle classification data collected over time. Now moving our attention to the actual weight distributions. Actual weights are important in calculating pavement layer responses for pavement design, both for flexible and rigid pavement design, and determining whether a design strategy is acceptable for the traffic conditions along the roadway. The axle load distribution factors are derived from the weighing and motion data. There are different WIM devices that collect axle weight data as well as vehicle classification data. The two examples shown on the slide are for different vehicle class distributions. The upper graph displays the single axle load distribution. Y-axis is the normalized axle load distribution for the single axle load intervals. For truck vehicle classes 5, 7, and 9. While the lower graph displays the same type of information, but for the tandem axle weight intervals, and for vehicle classes 9, 11, and 13. As shown, the class 9 distribution on the solid, the class 11 distribution with the X's, and the class 13 axle weight distributions for the class 13 tandem axles. So as displayed, there are many input variables of axle weight to determine the impact of trucks on pavement performance. And we'll come back to these axle weight distributions in terms of their importance and what a user should look for later in this module. Axle weight spectra distribution factors. As a reminder, section 8.1.2 axle weight distributions are provided on page 97 of the MEPDG Manual of Practice. There are 5 default axle weight distributions that come with the software for the designer to select from. And those are listed on page 97 of the MEPDG Manual of Practice. Those are defined or illustrated here separately. So the first is the NCHRP 137A. These were the default normalized axle load spectra that were developed under the NCHRP projects. They represent and are suggested for use for highways with a higher percentage of overloaded trucks. In other words, if we have a higher percentage of overloaded trucks exceeding the axle weight limit, then the NCHRP 137A default distribution is encouraged for use. The next three were derived from the long-term pavement performance program, using sites that were considered very valid and where the WEM device has been continually calibrated and maintained. So there is a very comfortable feeling that the axle weights measured are accurate. So the first is defined as heavy. These are typically freight routes, can be rural and or urban interstate routes with an AADTT exceeding 2,000 trucks per day. These are suggested, the heavy freight routes are suggested for use on rural roadways that serve significant long-haul truck movements. The next is defined as typical, a typical axle load distribution. These are non-freight routes, can be urban and or rural routes with an ADT greater than 1,000. Highways, and these are highways that serve a mix of urban and long-haul truck movements itself. The third of the LTPP global default values is defined as light. These are also non-freight routes that can be urban or rural routes, but with an AADTT less than 1,000. These are rural and urban highways where more than 70% of the trucks are not fully loaded. These are usually short haul routes of truck movements. The final category user can select from is referred to as global. This is similar to the typical route determined from the LTPP and basically is an average of many LTPP WEM sites. These are the user would select global for highways that serve a mix of urban and long-haul truck route movements. This slide includes a graphical comparison of the 5 default tandem axle distributions suggested for use, which were defined in the previous slides. So these are defined in the previous slide, or this slide here, and then these are illustrated in the 2 graphs shown on this slide. Basically, the NCHRP, also this is specifically Class 9, and it's tandem axle load interval groups for both the upper and the lower graph. And this is the percentage of axles within each load interval. The difference between the upper graph and the lower graph is that the lower graph is an expanded image of the trucks between about 32,000 tandem axle loads to 50,000 tandem axle loads. So it's an expanded version of these load intervals in the upper graph. So we show that going below, looking at the lower graph first, the NCHRP 137A graph is basically the blue diamonds showing the axle load distribution or the normalized axle load distribution. The LTPP global or the open circles and that's this distribution. See, the LTPP heavy default distribution is the open diamonds, and the open diamonds are similar to the or the open diamonds is the dashed line here. So there's a difference between the LTPP heavy, which has a higher percent of axle loads near the legal load limit, but the NCHRP 137, that's the triangle, the diamonds for the NCHRP 137A has a much lower percentage of the number of tandem axle vehicle class 9 trucks at the legal load limit, but have a higher percentage to indicate a much higher percentage of overloaded trucks above the legal load limit. And then the open circles are the typical axle distribution, and the X's are the LTPP light distribution, or defined as the light distribution. So this is an example for the normal axle load distribution for tandem axles developed for a specific agency for use in design. These axle load spectra are the agency's default normal axle load spectra in comparison to the tandem axle legal load limit. So this shows what's defined as a heavy axle load 1, heavy axle load limit 1, heavy axle load limit 2, very heavy axle or very heavy load limit 1, very heavy load limit 2 in comparison to the legal load limit for this roadway, as an example. And this is just displaying the normalized axle load distribution factors that are used in Pavement ME for the different axle load intervals and the percentages of those axles within that axle load distribution. Now, to illustrate the importance of axle loads, especially the number of heavy overloaded Class 13 axle loads, this slide shows an example where there is a higher percentage of overloaded trucks in one direction, and the other direction the axle loads were within the legal load limit. Many of the trucks were unloaded for this one direction. The graph compares the predicted bottom-up alligator cracking for basically 3 runs. The first run is to use the default values defined as the solid circles. That's the default axle load distribution. Run 2 was use of the unloaded or lower than legal load limit in an opposite direction. So this is the southbound predicted amount of bottom-up fatigue cracking where we have a higher percentage of unloaded trucks. The third run was the use of the overloaded trucks in the northbound direction. That's the X's, northbound that are overloaded or have a higher percentage of overloaded trucks. And this is the predicted bottom-up alligator cracking over time. So you can see that the overloaded trucks become very important, even though the number of trucks are the same, whether they're overloaded at the legal load limit or around the legal load limit or have a substantial that are unloaded, makes a big difference or significant difference in the amount of alligator cracking. The same would be true for rutting. The same would be true for the percent mid-slab cracking in a jointed plain concrete pavement. This kind of also shows that if we have, say, a 20% criteria for bottom-up fatigue cracking, the overloaded direction would have about a little over maybe 6 years of a design life. The average, if we combined everything, or if looking at the typical average, we would have about slightly over a 20-year design. And then if we had used the unloaded or predominantly unloaded truck traffic, we would significantly have maybe a 20-year design life. The average value would be about a little over 10 years. I think I said 20, but it would be a little over 10 years design life. So this does make a big difference. So overloaded Class 13 trucks will reduce the life of the pavement by about 40% related to cracking. So it's very significant. Now let's look at an example of an axle load distribution impact on design. So the question is, in looking at the normalized axle load spectra, for the class, for tandem axle weight interval, for a class 9, 11, and then class 13. The axle load distribution for truck classes 4 through 13 have a large number of inputs when considering the axle load, axle type, and different truck classes. So should we require all loads are measured at the same precision in capturing the axle load data? In other words, for all classes, truck classes, and all groups that go from a class 4 to a class 13, should they all have the same precision? Initially, we would say yes, because being more accurate is always perceived to being more reliable or better. However, in terms of predicting the stress, that increased precision, is it worth the cost for measuring those light axles or axles with light weights? So to answer that question, we will look at, we'll have 3 WEM sites. And again, this shows 3 normalized axle load distributions are shown on these slides from 3 different WEM sites that were included or collected from the Long-Term Pavement Performance Program. So these come directly from the LTPP program. The top figure shows the full normalized axle load spectra, while the bottom figure shows only a portion or expanded portion of the normalized axle load distribution factors near the legal load limit for the tandem axle loads for a class 9 truck. So we have a WEM site number 1. It shows the tandem axle load distribution for a class 9 truck. We then have WEM site 2 showing the same thing. And then we have WEM site 3, which also shows the same data. Percent of tandem axles within the tandem axle weight intervals. The bottom graph simply shows an expanded version near and beyond the legal load limit. So the WEM site number 1 is the open diamonds. WEM site number 2 is the WEM site triangles. WEM site 2 is the closed diamonds. And WEM site 3 are the cross X's in terms of the load distribution. And as you can see up in the upper graph, WEM site 3 near the legal load limit has a much higher percentage of Class 9 tandem axle loads near the legal load limit, while Site 2 has a much lower percentage of axle loads, Class 9 tandem axle loads, but then has a higher percentage of higher tandem axle loads above the legal load limit. So the question becomes, which of these tandem axle load distributions will do more damage to a pavement, whether flexible or rigid? So before we go on to the next slide, we'll pause here for a minute for trying to interpret from the user which of these WEM sites would impose the greater amount of damage to our pavement. Is it WEM site number 1, WEM site number 2, or WEM site number 3? This slide or group slides includes graphs that show the results of the predicted rut depth, alligator cracking, and IRI between the 3 WEM sites. So these are the predicted asphalt pavement distresses for the 3 axle load distribution provided in the previous example. These 3 WEM sites. Okay, so with rutting, rut depth as a function of the number of truckload applications. And this shows the triangle, closed triangles. WEM site 2 predicts the greatest amount of rut depth, total rut depth. WEM site 3 and 1 have about equal predicted rut depths. Alligator cracking, bottom-up alligator cracking, shows WEM site 2, the closed triangle, predicts much more fatigue cracking, and WEM site 3, the open diamonds, predicts slightly more of bottom-up fatigue crack than WEM site number 1. IRI, WEM site number 2, the closed triangles, predicts a greater IRI over time, and WEM site number 3 and number 1 have about the same predicted IRI over time. So in result, WEM site number 2 results in more damage or distress, and that would be the case for flexible pavements, as shown in this slide by these graphs, as well as for jointed plain concrete pavement in terms of percent cracked slabs, or also for continuously reinforced concrete pavements in terms of the number of punch-outs per mile. So the WEM site with the higher number of heavier loads, the percentage of the higher percentage of overloaded trucks, have greater distress, even though they have small differences between the distributions within this range. The focus of this discussion is to emphasize that big differences between 2 weight distributions may result in small differences, while a very small difference in weight distributions may be very significant, especially when those weight distributions are for the overloaded trucks. So simply looking at the percentages of trucks at the legal load limit, where WEM site number 3 had a higher percentages, would not be the case to define the higher distresses when WEM site 2 had slightly higher percentages of significantly overloaded trucks. So, do we have to have the same precision through all load levels for pavement design? The answer to that question would be no. We'd want the higher precision at the higher load levels to ensure we have an accurate representation of the normalized axle load distribution factors from basically the axle load limit to include overloaded trucks that we know occur on our roadway system here in North America. So in summary, the order of higher predicted fatigue cracking and distresses: WEM site number 2, then WEM site number 3, then WEM site number 1. And basically that corresponds to the number of overloaded trucks. Now, lateral wonder of trucks. Truck wonder relates to or defines the lateral distribution of trucks across the lane widths and becomes very important for Portland cement concrete pavement design because of the edge stress condition. It's also important for flexible pavement design because the critical layer response are wheel load dependent and how the loads get superimposed in terms of the distribution. The truck wander or lateral distribution is assumed to be constant between all truck classes, and the default value is 10 inches. This is the standard deviation of wheel loads along the mean wheel load path. In other words, the distribution of where the outside wheels are located from the trucks relative to the edge of the pavement. For rigid pavement design, the location of the edge of the outside of the tire is 18 inches. That's the default, assumed to be the default value. The location is important for rigid pavement design because the closer the tires are to the edge of the slab, the higher the tensile stresses. So the greater the standard deviation of the wheel loads for rigid pavements, the closer some of those loads are to the edge of the pavement. The lane width is also needed for rigid pavement design. Lane width and the mean wheel location are not needed for flexible pavement design. But the standard deviation of the lateral distributions of the wheel loads or axles are important for both flexible and rigid pavement design. And this on the schematic on the slide shows the typical location of the edge of the outside tire to be 18 inches. The edge of the tire versus the edge of the slab or the edge of the lane marking, if the lane marking also includes a widened slab. So it's the edge from the lane marking or the to the edge of the tire itself. Axle configuration. Axle configuration data are obtained from the WEM data or weighing in motion data. This slide shows and lists the truck axle configuration factors that are obtained from the WEM data and used by the Pavement ME software. We have the number of axles per axle type, axle spacing, and then the wheelbase for different types of trucks that operate along the facility, and these would represent average value that are determined from the WEM data. And the number of axles per type is dependent on the truck classification. So the number of axles, type of axles, whether it's one tandem, a single, and a single steering for this truck. For this truck, it's two tandem axles and a steering axle. This truck has a tridem, a tandem, and a single steering axle. And this data is collected for the different truck classifications, and then that data is averaged to determine the number of axle types, and then the axle spacing, and then the wheelbase. The default axle spacing and the wheelbase are all defined in the manual of practice, and that was under Chapter 8.1. So 51.6 inches is the default value for tandem axles. The spacing between the spacing of a tandem axle, 51.6. 49.2 inches is for the tridem axles, and then also 49.2 for any quad axles. The defaults for the wheelbase inputs and length and the percentage of trucks within each wheelbase are 12 feet, or they're given in the manual of practice, but they're 12 feet for short wheelbases, and 17% of the trucks are assumed to have a short wheelbase, 15 feet for medium wheelbases, and 22% of trucks are assumed to have a medium wheelbase, and 18 feet for long wheelbases, and it is assumed that 61% of trucks have a long wheelbase. So those are the default values. The number of axles per axle types are shown in this slide, and are the default values included in the MEPDG manual of practice. These were derived from an analysis of the truck traffic WEM data for many long-term pavement performance sites. This is also assumed to be constant over time. In other words, the number of axle load types do not change over time. So this slide shows and lists the truck factors that have an effect on pavement performance but are not obtained from WEM data. The default values for these input variables were obtained from truck and tire manufacturers for the common trucks in use on the roadways in North America. So they may not be applicable to special trucks. The default values represent the average values, which were obtained from the more common trucks and more of the common tire types that are used on those trucks. The default value for the axle width for rigid pavement design is 8.5 feet. The default values for the dual tire spacing, in other words, that's the spacing between the duals of an axle, is 12 inches. And then the default for the hot tire inflation pressure is 120 psi. And again, the tire pressure, the dual tire spacing, the axle width are assumed to be constant for all truck types. This is a schematic of the axle configuration, which is defined by 5 different parameters or input variables. These include the average axle width, outside edge of the tires on opposite ends of the axle, the spacing between spacing between the axles or the wheelbase, the spacing between the axles within an axle type, duals, not, tandem, tridems, and quads, which is the axle spacing, the spacing between the duals, and then the tire pressure. These are defined, each one of these is defined in the manual of practice itself. So let's quickly review some truck traffic limitations of the Pavement ME designed to simulate all types of trucks and or tire configurations that are being used on the roadways typically found in North America. So these next slides provide a listing of some of the limitation when it comes to the truck traffic features and input variables. So the first item is Pavement ME cannot directly include super singles. In other words, we don't have duals, we just have a single tire on each side of the axle, or sometimes referred to as wide base single tires within the traffic stream. Those can still be a single axle, a tandem axle, or a tridem axle, or even quad within the truck mix for pavement analysis, other than through the special truck traffic analysis, which is not covered in this workshop. So the super singles or the wide base single tires are not directly simulated within the Pavement ME software itself. They can be simulated if we assume a dual tire spacing. In other words, if we assume the dual tire spacing between the two tires to be 0. So both tire loads are then applied to the same tire. The Pavement ME cannot simulate non-uniform contact pressure, which we know we have with the super singles and our wide-based single tires. This does definitely have a non-uniform contact pressure, and even with some of the standard tires where we have a dual tire on our single tandem or tridem or quad type axles, there is a load distribution, contact distribution under that tire. That is not simulated with Pavement ME. So we use the hot inflation tire pressure to represent the uniform contact pressure. The third, for flexible and semi-rigid flexible pavement analysis, does not use the hourly distribution of truck traffic. So we cannot determine the damage from trucks only operating during portions of the daytime and or nighttime hours. In other words, the temperature of the day or not the temperature of the day, but the time of the day is assumed to have an equal percentages of trucks for flexible and semi-rigid pavement analysis. Another limitation is Pavement ME cannot directly consider the impact of construction traffic on layer deterioration or damage, especially rehabilitation where the roadway is opened during construction and heavier trucks to deliver materials to the roadway, i.e., as an example, the asphalt delivery trucks delivering the mix to the paving, and those trucks are riding over the in-place asphalt layer. That is not simulated in the Pavement ME, even though for some lower volume roadways, that can be relatively damaging to the existing pavement, even though it doesn't have many load applications. So, in other words, or in summary, we cannot consider stage construction or construction traffic for layer deterioration or damage. And it has to be considered independently. So cannot directly simulate effective traffic on individual layers placed during stage construction. So now let's go through a quick summary of the traffic input variables. A summary of the default values of traffic input variables for all pavement types. There are 17 normalized volume distribution called truck traffic classification groups that we discussed and are included and defined in the MEPDG Manual of Practice that the user can select from. There are also 5 normalized axle load spectra or distributions in the software that the user can select from. The standard deviation of the lateral wander is 10 inches. Dual's tire spacing is 12 inches. The tire pressure is 120 psi, and these were all used as default or considered default values and were used in the most of the global calibrations that were done for the distress prediction transfer function. And then the axle spacing for tandem, tridem, and quads. Kind of as a reminder also, the following traffic input variables only used in rigid pavement design. Hourly distribution factors, distance between the slab edge and edge of the tire. Again, the default value is 18 inches. Design lane width, axle width, and the default value is 8.5 feet. And then the truck wheelbase, and the default values for the short, medium, and long truck wheelbases are listed on this slide. So we listed and reviewed the truck traffic inputs required for Pavement ME Design. We then explained how to determine the truck traffic inputs and where some of those inputs are going to come from and which ones are readily available as default values in the Pavement ME software. We described the simulation and impact of truck traffic on pavement distress and design, especially looking at the axle weight distribution and the importance of overloaded trucks. We identified some limitations of the Pavement ME software related to truck traffic, and the hourly truck distribution factors, wheelbases, and distance from the truck edge are only needed for rigid pavement design. So that concludes Module 4.3 on the truck traffic inputs. The next section that we will overview or present will be Module 4.4 on the material layer properties for use in the Pavement ME software.